All right, our last unit, relativity, well, modern physics, but we'll look at mainly relativity, and then the other sort of half of this is sort of an introduction to quantum mechanics. Um, so, yeah, really to understand relativity, we go back to something we've talked about before, and we're going to see just how important this concept is. Yeah, so that's why it says, like, even right here, like, recall, because we've talked about this stuff before, and it is a little bit weird to sort of define. Like, it's you use these terms a lot, like anything, right? And you sort of just have an innate sense of it. Sometimes it's even harder to define. So you could say though that a frame of reference, um, you could say, okay, well, basically it's a coordinate system, right? That's kind of a key piece of it, right? Is that you've got some sort of coordinate system, and relative to that system you can describe motion or whatever you want, right? You can do physics. um, and so an inertial frame, which is really key here, is one that is not accelerating. That is, if you know one thing about an inertial reference frame, know that it is not accelerating, right? And if it's not accelerating, that means that the velocity is constant, uh, which could be zero. It's always convenient if it's zero, but it's constant. And the net force is zero, which is probably right. Right, that's a big part of this thing here. Oh wow, the internet must be slow here. The central claim of special relativity is that, and this really is important, right? All inertial frames of reference are equal. I'm trying to underline it, but there you go. That's it. If you really understand that and take that really seriously, then special relativity is not that challenging or difficult to get your head around. The problem is that is a really, really difficult concept to like fully internalize. Right? Because it doesn't feel that way when you look at a lot of actual situations. But if you can believe that, then not a big deal, right? And that's sort of another way of saying this, or something that's important. Not to just read everything, but if you really want to take that seriously, then what you have to realize is that no one frame is correct, right? If you've got, someone on a train, I don't know why I'm doing it like this, but they're on. Here's my weird train, and it's moving right with some speed v relative to the Earth. You have to say that from their perspective, right, the Earth and everything is moving under them, right? You can't say, well, no, Earth being the observer on Earth, looking at this, that's the correct reference frame, or that's a more important, or somehow like tied to more of a universal system. Like there's no one frame is better than the other. It is equally as correct and useful depending on the situation to say no. The person on a train, like, to really get yourself in their perspective and say no, they're at rest, they're not moving, and everything else is moving relative to them. Let me get rid of all this. And that brings us to this idea here, right? A universal coordinate system. It was thought for a long time as, you might think, well, there's got to be some sort of universal coordinate system, right? There's got to be like what they call an ether. That is to say, like, we know that the Earth is rotating and it's going around the sun, and the sun is going around the center of our galaxy. And that's moving relative to our local group, and then there's even a supercluster and all that, but there's got to be some grid, if you will, that you could put in space, and everything is moving relative to that grid, right? It sort of feels like what should be true. And they actually tried to test this idea. This is a quite famous experiment. Maybe you can look up more detail. I don't want to. But this Michelson-Morley experiment, this was 1887. And essentially what they did was they based this experiment on this idea that, look, if we're moving through this, universal coordinate system, then as the Earth is rotating, right, which it is, we must be orienting ourselves differently, right, around this coordinate system. And depending where we are at any one moment in time, maybe we're going with that coordinate system, right? And maybe in some other direction, we're not going with that as well. So they essentially designed what they basically, you have a coherent light source, right? So you shoot out a beam of light here, and then you've got the idea here is that when the light reaches this mirror, which is angled here, right, roughly half the light goes through and hits this mirror over here, and the other half gets split and goes and hits this mirror. Now, just like when we did stuff with thin films, you have to imagine the light is basically going straight to each mirror and back, which is just showing you a little bit of space here. So again, if you assume, or if you take, believe that, and I don't know why you wouldn't if you hadn't really tested it. Again, suppose we're actually going through, the ether with some speed in this direction, right? Not the other direction, right? Well, that's going to change the time it takes for the light to go to hit this mirror and come back. You're going to be going with this, you're going to be going with the Earth's direction of motion when the light goes this way, but then when the light comes back, it's going to be going against it, and that actually will make it take a different amount of time to go there and back than it will for light to just go up and down, right? It'll change. There isn't, you can do the calculation and figure out what the time difference should be. And what that will mean is that the light will be out of phase, right? Because then you've got your detector here. So remember, the light gets split when it reaches this mirror. Some goes up, some goes this way, but then it also comes back, and then together it goes to the detector, right? And so if the light has taken longer to go to one mirror than the other, there should be some sort of phase difference here. And of course, they detected nothing, right? It was completely in phase. Now, interestingly, more current experiments that aim to test gravity, right, or gravity waves, somewhat use a very similar thing, and they actually do detect a little bit of a difference, but that's on a bit of a different scale, and they actually have different ones at different positions on the planet, just to contrast them and actually see that is some sort of gravity wave. But nonetheless, at that time, that was sufficient to say, yeah, wow, there is no universal coordinate system, and so you really have to take that seriously and sort of, try to really believe it, convince yourself, yes, this is absolutely true. There is no universal coordinate system, right? If we have someone traveling by the planet on a spaceship, it's no more correct to say that they are moving with a speed v than to say they are stationary, right? They're not moving at all, and we are actually on the planet moving past them, right? You just have to be able to go from one coordinate system to the other, more importantly, from one inertial frame of reference to another. All right, so the diagram to the right shows the perspective of two observers in an inertial reference frame. Which observer is moving? From the poll, the class seems a little bit split here, but and this one certainly, right? You see observer, you just feel like, you see the guy here on a trolley car, it just feels like he's moving. But then you look at here, reference frame one. This is his reference frame, right? He's just standing there throwing a ball up, straight up in the air, and it comes back down. Maybe the planet is rotating underneath this thing. Maybe. But this is, for all intents and purposes, an inertial frame. And same thing here, observer 2. And you can see we're drawing a coordinate system here with that observer, just as we did over here, right? There's a coordinate system that you can think of as sort of being attached to the trolley car. So this is one of those questions that would have a more of a tricky, nuanced answer, because you could say either could be moving relative to someone else, but the important thing here is that in their own inertial frame, neither are moving. Postulates down here, right? So really, Einstein put this together into two postulates, right? Two claims, if you will, that just all the math and everything kind of follows from this. So postulate number one, the principle of relativity, the laws of physics are the same in all inertial frames, right? So that even takes this example we did a step further. It says not only can you say that each observer is at rest in their own inertial reference frame, right? But more importantly, all the laws of physics, any experiment that you do in your inertial frame, you're going to get the same results, right? And then postulate two, the speed of light is constant in all inertial frames, right? Sounds simple, right? Two things. All inertial frames are equal. Speed of light is the speed of light. Let's see. A spacecraft travels by Earth at 0.9 c. So when I write something like 0.9 c, right, that just means like 90% of the speed of light, you could say, right? All right. Just whenever you see that, it's sometimes a convenient way to write something as a percentage of, or I guess in this case, a fraction of the speed of light or whatever. So 90% of the speed of light, that's pretty good. They're traveling by Earth toward the sun. How does the speed of the sun's light differ for an observer on Earth relative to one in the spacecraft? We could draw this here, right? We got the sun, and we got, rays of light from the sun. And so if you're on Earth, right, maybe we see light coming to us, right? Right, if you're standing here on the planet, and I guess you're quite big here on Earth. And then we got someone on this spaceship. Oh, it's not fixing that anymore. Another thing that has happened since our spaceship is just a box here, but this is going past us at v equals 0.9 c. And so for someone here on the spaceship, what are they? I mean, it seems like you want to look at this like classical mechanics, right? You want to look at this and say, well, let's suppose the person here on Earth is at rest relative to the sun, right? I mean, going around it, but we're talking speeds this great, we might as well just say they're at rest, and they see something, an object coming toward them, in this case, light, at the speed of light. So if you have, in this case, a ship going this direction at 0.9 c, then, what speed should they see the light coming toward them? And again, but that's the postulate. That's the idea, is that they see, right? They see the light coming toward them at the speed of light. I'll say they see light from the sun coming toward them at C. I'm going to do the decimal. Now, I think most of you could probably answer that if I look at the poll that I did. Most people said that, essentially. But can you really believe it, I guess, is the real trick. Right? Can you really see that, like, okay, because that seems to maybe lead to some other inconsistencies. And again, if you're dealing with speeds that are much, much slower, right? If I said, someone's over here where the sun is and they throw a ball toward this person with some speed, well, then this is absolutely different, right? Whatever the speed of the ball is, right? If there's someone throws a ball, let's say here, 10 meters per second, and this person here is going 5 meters per second, right? Then, right, they see the ball coming toward them at 15 meters per second, right? You add them. So in this case, you might want to do that and say, well, shouldn't they see the light coming toward them at 1.9 C? But they don't. And that's why things are so different once you get to speeds that are closer to the speed of light, which, again, is pretty hard for us to um, really appreciate because we just never really experience speeds like that.